Okay, so let's continue on now with how do we do these calculations and how do we figure out what all these energy levels are. So make sure you have your calculator with you if you don't already have it ready to go. So first of all, let's just remember that we know this formula. The speed of light is frequency times wavelength. And so therefore, since energy is h times frequency, and frequency is c over lambda, then that means that the energy change between any two orbitals, any two transitions, will be hc over lambda. So that will allow us to figure out what the wavelength is for any of these photons that are given off. So for example, if I transition between the n equals 3 down to the n equals 1, if I can figure out what that energy change is, then I can set that equal to hc over lambda and solve for lambda and figure out what wavelength that corresponds to. That's what wavelength of light is being given off. Or if I jump from the 3 to 2 level, that's going to be a different change in energy, and so therefore I would have a different wavelength being given off from that. And I can calculate that using this formula. So this is the formula that's going to allow me, if I know the energy changes, that's the formula that's going to allow me to figure out what wavelength each one of those are. Now, how do I figure out what these energies are? That's this formula down here on the bottom. The energies are given by a simple formula for each level, depending on which n you're dealing with, n equals 1, 2, or 3. You take minus 13.6, which is the basis for the hydrogen. You multiply by the atomic number squared and divide by the energy level squared. So Z, just to remind you, I don't know what you guys used, that's the number of protons in the atom. It's the atomic number, the number at the top of the periodic table. For hydrogen, Z equals 1. For helium, Z equals 2. For lithium, Z equals 3, whatever. So you have to know what's the atomic number of your element. That's how you will go ahead and figure out what your various energy values are for each of your levels. So now, if I know that I'm in an atom that has a Z value of 7 electrons, 7 protons, then I could put 7 in for the Z and have 7 squared, and then I could figure out what the energy is for each of my levels. And so then if I transition between any two of my levels, I can figure out what that transition is, and therefore I can figure out what the wavelength is that's given off for those transitions. The last little formula here is in the middle. You don't use it as often, but it'll tell you what radius those particular orbits are happening at. And so this is the smallest radius of the hydrogen atom, and then you multiply that times the n squared and divide by Z, the atomic number. Alright, so we're going to use hydrogen as an example. We'll do an example with hydrogen on the next slide. So here is the hydrogen atom. The first thing they're asking you to do is figure out the energy level of each of those, the energy amount of each of those levels. So the formula was E of n is equal to negative 13.6 times Z squared over n squared. Now for hydrogen, Z is 1. So basically I'm going to have minus 13.6 divided by n squared for each of these n values. So for the n equals 1 value, it's just going to be minus 13.6 electron volts. For the n equals 2, it's going to be minus 13.6 divided by 4. For n equals 3, it's going to be minus 13.6 divided by 9. So you can see how I'm doing this, and then minus 13.6 divided by 16, and all of those various things, right? So I'm going to go ahead and figure those out. So 13.6 divided by 4 is equal to 3.4. So this is negative 3.4 electron volts. Pardon me, that's 3.4 electron volts. And then 13.6 divided by 9 This is negative 1.51 electron volts. 13.6 divided by 16 is 0.85, negative 0.85 electron volts. And if I were to take 13.6 and divide by infinity, I would get 0, which is, this is the ionized state. This is the free state of the electron out here. Okay, so that's the first thing you have to do when you're working a problem, is you have to figure out what these energy levels are equivalent to, so that when I make transitions, I'll know how much energy is involved. So now they say determine the wavelength of light emitted when an electron jumps from the n equals 2 to the n equals 1. So n equals 2 to n equals 1 is an energy difference of 13.6 minus 3.4. So if I calculate what that is, 13.6 minus 3.4 is 10.2 electron volts. So that's the energy difference for that particular jump. Now to figure out what that wavelength is, I'm going to set that energy difference equal to hc over lambda. And that's going to allow me to calculate this. So since my energy is in electron volts, I'm going to use the h value that is in electron volts seconds. If my energy was in joules, I would use the h value that has the joules. So this is going to be equal to 4.13 times 10 to the minus 15 times 3 times 10 to the 8th, and then divided by the wavelength. So I'm going to solve for the wavelength. So I'll do 4.13 times 10 to the minus 15 times 3 times 10 to the 8th, and then I'll divide by 10.2. And that gives me a wavelength of 1.214 times 10 to the minus 7 meters. Okay? Which is about 121 nanometers. So that is not something we can see. 121 nanometers is not in a wavelength that we're going to be able to visibly see, but it's something in the, it's in a different range. It's shorter than what we can see, so it's going to be in the ultraviolet range. If we do the n equals 4 to n equals 1, that's this one right here. So 4 to 1 is all the way this jump. That change in energy is going to be 13.6 minus the 0.85 that the 4 was. I think that was 0.85. Yes, it was. So that gives me an energy change of 12.75 electron volts. And then I can set that equal to hc over lambda, the same as I did before. So that's 4.13 times 10 to the minus 15. The c value is 3 times 10 to the 8th still. And there's my wavelength. So I can solve for this wavelength of light that would be given off. And that's going to give me 9.71 times 10 to the minus 8 meters, which is about 97 nanometers, I believe. So that again is not something we're going to be able to see. Alright, what I do want you to note is that the lesser energy changes are going to give you the longer wavelengths. So the lesser the energy change, the longer the wavelength. So this was a lesser energy change, and the wavelength was about 121 nanometers. If I want to get into wavelengths that I can see, I'm going to have to do energy changes that are like these right here, that are even less. So because your lesser your energy is going to correspond to a longer wavelength being given off. Okay? All right. So we're going to do a few more examples. I'm actually going to ask you guys to do these on your own. How much energy is needed to ionize an atom? That means you have to take it from the n equals 2 state, which remember the n equals 2 I believe was negative 3.4 electron volts, I think was the energy for that. You have to get it completely out of the atom. So you're going to take it from n equals 2 out to the n equals infinity, right? So you're going to completely take it out of the atom. So you can figure out how much energy you would need to do that. And then if I was a hydrogen atom in the ground state, and this is the second question, and I needed to be ionized, you would have to put in 13.6 electron volts of energy to do that. And they want to know what wavelength of light that corresponds to. So if I had to shine light onto this hydrogen atom to get this electron to jump up, what wavelength of light would I have to shine onto the atom to get it to jump? This one here we're going to do together. The helium atom that makes a transition from the 6 to the 2 state, and it gives off a photon in the process. The first thing they want us to do is calculate the energy of each state. So you have to look up helium. Helium is Z equals 2. So I'm going to draw this out for helium. Okay. So here's the ground state of helium, the n equals 1 state. The energy for that is going to be negative 13.6 times Z squared, which is going to be 4, divided by n squared, which is 1. So 13.6 times 4 is negative 54.4. So that's the n equals 1 state for helium. The n equals 2 state is going to be minus 13.6 times Z squared divided by n squared. So that's just going to be minus 13.6. And I could go ahead and do the 3, 4, and 5 state if I wanted to, but I don't think I need them for this one. So I'm just going to draw them in here and not calculate them. But what I will need is the n equals 6 state. So 3, 4, 5, 6. So the energy for the n equals 6 state is negative 13.6 times the Z squared, again, is 4. And this time the n squared is 36 on the bottom. Okay, so 13.6 times 4 divided by 36 is negative 1.51 electron volts. So they want to know what is this transition from n equals 6 down to n equals 2. Oh no, let's see. Right. So if it transitions from 6 to 2, what energy difference is that? So that's an energy difference of 13.6 minus 1.51. Which is an energy difference of about 12.09 electron volts. And then the question is, that photon, would it be able to be absorbed by hydrogen? So you have to go back and look at hydrogen and see, is there a transition that from 13.6 to 1.51 in the hydrogen? And there actually is, I believe. If we think about hydrogen, the n equals 1 state is 13.6 electron volts. The n equals 2 state is negative 3.4 electron volts. But I believe the n equals 3 state is the equivalent of this one here, I believe, which is going to be equivalent of 1/9, so 1.51. So it would be possible, if this photon was given off, it could be absorbed by hydrogen, and that would cause a jump from n equals 1 up to n equals 3, because it's the exact amount of energy needed to go between that. So would the jump happen? Yes, it would. It would go from n equals 1 to n equals 3, because it would be exactly the 12.09 electron volts needed for that jump to happen and for that jump to occur. All right, so other than the other two, that should be the end of this one. And you should be ready to go tomorrow with some AP problems from previous tests.